Draw the products. Maybe the first question to ask, do I get 2 products or 1? Suppose we could get 3, right? There's a position there, there's a position there, there's a position there. But anisole here, we saw that although oxygen is electronegative and wants to suck electron density that way, it's not a meta-director because those electrons can jump down. So it's an ortho-para director. I'm gonna get lazy. I'm gonna get super lazy. All right, I'm feeling not so lazy. So there's our 2 products, ortho product and our para product. This is a ortho-para director. How do you feel about this one? So this is kind of a curveball because we're gonna talk about this today, hopefully. So what's my first product? Get a benzene ring down here. So our Friedel-Crafts alkylation, that's what that does. And let me just give you a heads up. If I did these in different order, I could control my product. Once we get into the slides, we're going to talk about side chain oxidation. And you realize from other things that potassium permanganate is a powerful oxidizing agent. Manganese is in the +7 oxidation state. And it will chew up an alky chain and give you a carboxylic acid. So this is we oxidized it with potassium permanganate. And then you'll recognize this as putting a bromine on the ring. Question is, where does the bromine go? Carbonyl carbons are what type of directors? Nope, they're meta. Because we discovered if we tried to put the Br in an ortho or para position, we'd get a carbocation eventually on this carbon, and the 2 positive charges doesn't like that. So there's our final product. So as I said earlier, if the order here was swapped and I did my bromination second, I'd get the ortho-para, and then we'd do the side chain oxidation, and we'd have this here in the ortho-para if I change this order. Things to pay attention to in the future. So here's where we left off Monday. And our previous little example where we had ethyl chloride, couldn't rearrange, and we nicely put a 2-carbon chain on a benzene ring. And so we saw this thing gets activated and it quickly rearranges. Here's a hydride shift. So here might be a way around that with the Friedel-Crafts acylation. So we call this a acyl halide. Here's the acyl group, some alky group there, and our Friedel-Crafts Lewis acid there. And so we can make a phenyl ketone. And so here's an example with acyl chloride, and we get this thing we're supposed to be able to name acetophenone. You could also call it acyl benzene. So instead of an alky chloride, we use an acyl chloride, and the product is a phenyl ketone that is less reactive than benzene. Because notice this is a deactivator. If we were to put another one on, it would want to go in the meta position, but it kind of shuts down. So we can get one product. Look at that, 95%. So what's the mechanism? Here's our acyl chloride, here's our Lewis acid, here's our complex. Those electrons jump there. So we get this acylium ion, which you might recognize from mass spectrometry. It's resonance stabilized. Then that attacks the benzene ring. We get our sigma complex, and then you imagine this comes down, pulls off that hydrogen, and that electron is going to reform the double bond in step 3. There it is, negative charge. I just think of it as a base. Actually forms some HCl, and we get our catalyst back. So Friedel-Crafts acylations are generally free from rearrangements and multiple substitutions. They do not go on strongly deactivated rings, however. That means you can't put a nitro group on and then do a Friedel-Crafts acylation. You can do the Friedel-Crafts acylation and then put a nitro group on. So when we ended Monday, or that first slide we shot today where we had propyl chloride and we didn't get our straight carbon chain. We didn't get that product. We attached the benzene ring to that carbon, do the carbocation rearrangement. But if we do our Friedel-Crafts acylation and amalgamated zinc, you put your amalgamated zinc in the flask with this and stir it up, and you start dripping HCl on it. And of course you get a bunch of zinc plus 2, and you reduce this double bond, or the carbonyl carbon, with 2 hydrogens there, and we get our straight chain alky group. The Clemmensen reduction is a way to convert acyl benzenes to alky benzenes by treatment with aqueous HCl and amalgamated zinc. Something similar is called the Wolff-Kushner reduction, and we'll study that in a couple weeks. So you've been exposed to the Grignard reagent, the cupric reagents a little bit. So aromatic substitution using these organometallic reagents, not so much the Grignard in here, but the Friedel-Crafts reactions have limitations, rearrangements, multiple acylations, and then if you just want a straight chain on a ring, you can do the Clemmensen reduction, but cannot occur on deactivated rings. We need strong electrophiles. So organometallic reagents can add alky groups to the benzene without these limitations. So our organocupric reagents, we've seen this before, where we have an alky halide, the basic building block of all organic chemistry, 2 lithiums, we get an organolithium compound. Of course, I get excited about this because I like to say, look at this here. Here's the most powerful base known to mankind. Carbon with a lone pair of electrons at negative charge. How do I know that? Because an alkane is the weakest acid known to mankind. All right, so this will react with copper 1 salts, like cuprous bromide or copper 1 bromide or chloride. 2 of these, 1 of those, and you get this R2Cu bromide if we use the bromide, lithium bromide. Lithium dialky cuprate reagents, also called Gilman reagents, can be prepared by the reaction of 2 equivalents of organolithium reagent with cuprous iodide. It's probably all iodide, even though with the X implies we could have the bromide. Not a big point there. So here's our lithium divinyl cuprate. The important thing is this bond here you're going to break. You're going to break this bond, and that's where you're going to hook it up to the benzene ring. So iodobenzene and this thing here, we formed a new bond between there, and we get styrene. So we can just as easily, if we had that alky halide and reacted it with the copper, we could make this the copper reagent. So once again, here's a halide, and here's this thing here. So we want to imagine forming a bond between here and there. So there it is. And these almost look like regular old substitutions. And you can probably, I would probably imagine like a pair of electrons there and just slamming it in there and the bromide leaving. And that's probably good enough to get you to the right product. But point number 2 here says it can't be an SN2 because viney and our real halides work well in this reaction. And just a point that all of our substitution eliminations had to deal with sp3 hybrid carbons. Clearly no sp3 hybrid carbons here. Probably a mechanism in which both these insert on copper and then slough off together, kind of analogous to the catalytic hydrogenation with palladium and platinum. It's beyond the scope of this course. The Heck reaction, and it uses a palladium catalyst, and right here we're not even seeing any benzene chemistry, but here is a alky halide, and here is a vinyl group. The important thing is we got this double bond here, and the palladium catalyst and the base So these things are palladium catalyzed coupling of an aryl or viney halide with an alkene. So here's our alkene, and we get a carbon-carbon bond at the less substituted end of the alkene. So we're going to put this thing right there. Triethylamine or sodium acetate is added to neutralize the H8H produced. So you see here this base is now protonated. Next up, the Suzuki reaction. It's also called Suzuki coupling, and we have a palladium catalyzed substitution that couples an aryl or viney halide with an alky or alkene or aliboronic acid or borate ester. So it's very similar to the Heck reaction, where we're going to form a new bond here and a new bond here and couple these things together. So imagine a palladium catalyst, and you got to start out with this boring. And so here's our R group. Now we got our R group on there. Here's an alky bromate ester, or we can start out with an alkyne. And here's a dialkoxy borane. And now we have this alkene boranoate ester. So we can use this thing or the acid. So to form those, here's two ways we do that, and can also be made by the hydrobornation of a double and triple bonds here. Now we get a look at the Suzuki coupling. So the question is, here's our viney halide, here's our boranoate ester. So we want to think of taking this and cleaving it, and that and cleaving it, and sticking them together. And we get both the E and the Z isomers. So now some benzene chemistry. It's in the benzene chapter. So here's our alky halide. Here is our bromic acid. So once again, if you think of this cleaving here and hooking up here, very much like a vinyl group. And there's our new carbon-carbon bond. Here's our coupling. Here's our coupling. So I wish I had the textbook. This is like a prescribed drug for something. I'd use my phone, but it's making the video. So notice, wow, 2 halides. Which one's going to couple? Well, fluorine is not always user-friendly, especially if you're a guy and you've eaten lots of omelets and pancakes from Teflon pans. Have you heard anything about that? Expect certain types of cancer later on in life. So we're going to cleave that and hook it up there. So there's the Suzuki coupling. So side chain oxidation. Here's a benzene, and we got a methyl group, an isopropyl group. Here's our potassium permanganate, and we see that the alky chains in both positions get oxidized away till there's nothing left but one carbon. Think about benzoic acid. Here's like a dibenzoic acid right here. And the nitro group is kind of already oxidized, and it just hangs out, and there it is, and oxidized all the way to the acid. Of course, you'll recall from your adipic acid experiment where you took cyclohexene, you had this in aqueous solution, and you had to add some concentrated HCl, then it precipitated out, and you were able to filter it. All right, so here's a ketone and a vinyl group. Potassium permanganate, it doesn't care any type of carbon side chain. It's going to oxidize it away. And our other favorite oxidizing agent would be dichromate and sulfuric acid, which becomes a chromic acid. So alky benzenes are oxidized to benzoic acid by heating in basic potassium permanganate or heating in this sodium dichromate in a solution of sulfuric acid. The benzylic carbon will be oxidized to the carboxylic acid. So this is the benzylic carbon, benzylic carbons. Side chain halogenation. So here's our two favorite. And you can almost think of this as being the allylic. If we drew a double bond there or there, of course the ring implies it's there. And we get a little bit of dibrominated product. So this thing isn't active. This thing is, because of resonance. So we only get halogenation at the benzylic position. And we learned this way back when, first semester. Chlorine is not as selective as bromination.